So further one we will start with the circuit model. Okay. So this is called a circuit model. What the actual thing is and what we are preparing the electrical equivalent model. Okay. The actual thing is that the metal wires are running inside the chip. Correct. The metal lines are running inside the chip. So that metal lines we are considering it as a RLC, resistance inductor and capacitor, RLC model. And because they are very close to each other, they are actually coupled with electromagnetic interference. Right? Because of the magnetic field interaction, that L12 will come. Because of the electric field interaction, that C12 will come. They are actually coupling, right? They are coupling the 1 and 2. Similarly, whatever the interconnect that is nearby, so all the interconnects we will definitely couple. But for first order analysis, we will limit it to only 2 interconnects. After that, we will try to exchange. Okay. So 2 interconnects I considered. So what drives the interconnect? Actually a transistor. Right? Actually, it is an inverter. Okay. So that's why I placed one inverter there, another inverter here. And what terminates? That is also inverter. Okay. So what I am saying is that this is also an inverter, but this interconnect will feed the inverter as a capacitor. Okay. This interconnect it will feed the inverter that is placed in here as a capacitor. That's why I kept as a capacitor. Okay. So this is the electrical equivalent model, and now we will see what happens if you pass the signal on one line. What you will see on the another line. So what it means? I excited Vx1 here. So obviously you get a rising pulse at output 1, and I applied a VDD here. Obviously you will see a 0 at output 2, but you will not see a 0. Okay. So that is the problem. You will not see a 0 here. You will see some noise. What is that you will see? That is actually called it as a crosstalk. Okay. Right? That actually called it as a crosstalk. What is the definition of crosstalk? A signal transmission on one line create the disturbance on the second line. Actually the second line wants to quiet. Because you applied a VDD here, it wants to stable at 0. It wants to keep quiet. But because of the capacitance and inductance existing here, okay, right, some noise we create on this line. So the definition of crosstalk you can write like this, you can say like this. Signal transmission on one line create disturbance on the second line. It is actually a crosstalk. Correct? And whatever the lines it will see, it may be on the top, it may be on the right, it may be on the left. Okay, it may be on the front, it may be on the back. So whatever the interconnects it will see, it will create a crosstalk everywhere. Everywhere nearby this reservoir. Okay. So because of the crosstalk, what happened? Basically, what happened? These are the effects that you will see. There may be a clock switching. There may be a change in propagation delays. Okay. So these are the impacts of crosstalk, right? And these are the types of crosstalk. One is functional and the second one is dynamic, right? What is functional crosstalk means? One line will switch. The first line will switch and the aggressor line wants to quiet. Okay? It wants to quiet. It wants to stable at 0. And the dynamic crosstalk means 2 lines will switch. Both line 1 and line 2 will switch. If 2 lines are switching in same direction, it is called even dynamic crosstalk. If 2 lines are switching in opposite direction, actually in fact this is low. Right? It is 1 to 0. It is not 1 to 1, basically there is a correction. So 2 lines are switching in opposite direction, it is called dynamic crosstalk in odd mode. And this is even mode, dynamic crosstalk in even mode, and this is functional crosstalk. Okay. So for this we can say that this is functional crosstalk. Why? Because only one line is switching, this is not switching, this is at 0. Now you see what is happening. Right? So there is a change in the signal, it is rising, it wants to, this line 2 wants to stable at 0, but it is not stable. You can see some noise is inducing on the line. So this is the noise that we are talking about. Okay. So this is the noise creating on the second line due to the signal transmission on the first line. Okay. So this is called crosstalk noise. Okay. The dark one. Okay. Right. I don't want to go in depth. That's why I don't want to explain what is the dot, what is these dots. I don't want to explain those things. Just I want to tell. We want to maintain a zero here, but it is not maintaining because of the crosstalk. Some noise is appearing. Right. That's it. And this is the work my supervisor developed in his PhD. Right. My supervisor developed a model for analyzing this crosstalk. Okay. So this is the actual model available in the literature, the red one. And this blue, the dark blue is the actual crosstalk that we actually observed in the interconnect. Okay. So this is the actual crosstalk that actually we observed, and this is the existing model in the literature. Then this is the model, this pink one. This is the model that my supervisor is developed based on the even odd mode technique. Okay. So he developed this model. You can clearly see that this model is actually capturing the SPICE results. Okay. Whatever the simulations you are getting, this model is more or less covering that, following the trend. Okay. So for this only he got the PhD. Right? He developed this model, he published it, he got the PhD. Correct? And what I did, I will try to explain later. Yeah. So this one I proposed, right? In my 4 years, I proposed this FDTD technique to capture the crosstalk, right? Finite difference time domain. This technique I proposed to capture the crosstalk, and we will see how this technique is developed, right? This is finite difference time domain technique, right? Is used to solve the transmission line equations in time domain. Okay. The strength of FDTD is we can solve the differential equations, right, with less number of assumptions. Right. Using this model, we can measure the voltage and current at any place, any time on the interconnect. It is not like that we can measure the output only at the power end. It is not like that. Anywhere you can take any point on the interconnect, you can measure the signal. Okay. So the basics of FDTD I will briefly explain, right? Very briefly explain. This is not you not get fully maybe in half an hour or 1 hour. Briefly explain. So first we will start with the Taylor's expansion. The basic mathematics knowledge you already have, right? The derivative of f of t naught plus delta t can be written like this, and derivative of f of t naught minus delta t can be written like this. From this, derivative of f of t can be rewritten like this with some assumptions, with some approximations here. So it means whatever the higher order terms you neglect. Okay. So the derivative of f of t can be measured like this. Okay. From equation 1 you will get this, from equation 2 you will get this. Okay. So this is from equation 1 t naught plus delta t, and this is from equation 2 t naught minus delta t. Done. If you do the center difference approximation, right, you take the average of these two. Okay. So f of t naught by f of t naught can be written as delta t naught plus delta t minus t naught minus delta t by 2 into delta t plus some approximations. These approximations we can neglect. Okay. So what I want to say that basically a derivative of a function can be described like this. Two different time intervals by whatever the time interval that you are taking. Okay. So this is called center difference approximation. Some numerical calculations I have done here. So there is f of y function. You want to do the derivative with respect to y. Okay. At y is equal to 2, right? The exact value is 24. If you substitute y is equal to 2, the exact value is 24. But if you do the center difference approximation, first equation you will get 26, second equation you will get 24.5. You do the average, the value is very near to the exact value. Okay. So this is the discretization in space and time domain. Okay. So there is a driver and this is an interconnect that we are talking about. For this interconnect, you segment the voltages and currents at different places. You don't measure the voltage and current at the same place and same time. Okay. So you need to show some discretization between voltage, time and current. Suppose this V2 is measured here and I2 is measured after some time, after some space. Okay. The same thing that I plotted here. This is the plot will show the discretization of time and space. For example, if you are measuring the Vk n, right, then Ik should measure here. Okay, not at same time. After some time, right? After some space. This k is different and this k is different. The space is delta z by t. Okay. This time is different and this time is different. This is n and this is n plus r. Okay. So you don't measure the time and space, voltage and current at same time, same space. Okay. But at the boundaries, it is obviously at same space. This is the near-end boundary, I0, I1, and this is the far-end boundary, V ndz plus 1 and I ndz plus 1. Okay. So boundaries at the same time, same space, but not in the interval. Done. So this is the thing that we are trying to capture. This is the circuit we are trying to capture the response. Okay. So this is a RLC distributed model. RLC distributed model. What is distributed model? You know, right? So the distributed model can be written like this. This is called RLC distributed model, right? Telegrapher's equations. Okay. It is a very famous code for microwave people. Those who are working in microwave, they know very well, right? Telegrapher's equations. So you write the telegrapher's equations for a transmission line, two transmission lines. This is voltage current for one line. Voltage current, second line. Done. Once these relations are with you, okay, you try to write a uniform equation, right? So these two equations you combine. Okay, this one and this one you combine, and this one you combine, like this. Where V is a 2 by 2 matrix or 2 by 1 matrix, R is a 2 by 2 matrix, L, C are 2 by 2 matrix, I is a 2 by 1 matrix. Okay. So like this you combine. Suppose there are 3 interconnects, so this will become 3 by 3 and this will become 3 by 1. Okay. So it is a uniform model applicable for all lines. That is what I want to show. So how to solve this equation we will see. Yeah. So now voltage we need to do the derivation with respect to Z. Okay. So what you do? You take two different values of V at k plus 1k with the space discretization of delta Z. Correct? And coming to the L, we need to do the derivative with respect to time. So what I suggest, you take two values of I at two different times. Okay. So this is two different space. Hope you understand, correct? This is space and this is time. Okay. K plus 1 is the space, n plus 1 is the time. So two different spaces by delta Z, two different time by delta t. Okay. So there is no discretization here. So you just take the average. No delta Z, no delta t, just an average. For this one, space discretization. So I is measured at two different spaces by delta Z. Time discretization. V is measured at two different times. Okay. So n plus 1 and n by delta t. Done. Okay. You got two equations. So the current equation you rewrite, you will get the voltage expression. This equation you rewrite, you will get the current expression. Okay, so this is the voltage that you are going to measure throughout the interconnect, and this is the current equation you are going to measure throughout the interconnect. So this is done. How to do the analysis of the interconnect is done. This part. Okay, from I1 to ndz. How to measure the voltages and currents, everything is done. Okay, only two equations. I solved only two equations. And the next one is how to measure the I0, I1 and I ndz plus 1 and V ndz plus 1. The boundary conditions we need to derive. Yeah. So this is a boundary condition. The near end is a CMOS inverter that we already defined, right? So you need to model this CMOS inverter. It is a combination of IP and IN currents. Okay, there is a combination of IP current and IN current that describes the I0 current. Okay, such that this I0 is described like this. You simply substitute K is equal to 1 in the previous equation, you will get this expression, right? And after rewriting this one, IN plus 1 half to IN plus 1 plus IN by 2, that is IN plus 1 half. And then you rearrange the equation, then you will get the current for I0. Okay? You will get the current for I0. Done? And next we are talking about the far end. Far end means is towards the load. So I NDZ plus 1. How to calculate? You simply substitute K is equal to NDZ plus 1. You will get this equation. Okay? You will get this equation, right? Because it is a capacitor, you can simply write C into dV by dt. I is equal to, it is just a capacitance current equation. I is equal to C into dV by dt. Okay? So because there is a time discretization again, discretization again. So we take two different times. This is n plus 1, this is n by delta t. So you will get I and dz plus 1. Okay? So all equations you have. What all equations? You have the equation for I0. We have the equation for I0. We have the equations for all these voltages and currents. We have the equation for I and dz plus 1. So once the equations are with you, then you use this flowchart. Okay. Then use this flowchart. Right? You run this code in MATLAB, then you will get the response. The voltage response you will get, the current response you will get. Okay. So first you start, excite the source, input source. Okay. And you compute the V1, you compute the VK, you compute the VNDZ plus 1, and you compute the currents. Okay. And continue the loop. So all these things in a single formula. Okay, where n is equal to 2 to nt, where nt is the number of time segments and nz is the number of space segments. Okay, after that you extract the waveforms. Done. Okay, close it. And now you see how what waveforms I got and how beautiful it is. Right? So this is, in this case, line 1 and line 2 both are changing in same phase. So this is even more. So this is the response I got from X-Spice, and this is the response I got from my model, MPPT model. Okay? Right? And this is the response I got in this switching condition. What is this switching condition? This is down switch. This is up switch. It means odd mode. Dynamic crosstalk in odd mode, and this is the dynamic crosstalk in even mode. So here also, X-Spice model and my FDTT model are exactly accurate. And this is also a dynamic crosstalk in out phase, in odd mode. Because these two switches are switching in two different directions, correct? So in this case also it is matching, exactly matching. Okay, the functional crosstalk also I will show you. So line 1 is down switching. Because it is an inverter, the output will rise. See, output is rising. Both X-Spice and models are correct. Functional crosstalk you can clearly see. It is down switching, and the second input is VDD. Actually, we are expecting a 0 in line 2. Line 2 we are expecting a 0, but you are not getting 0. Some noise you are getting. That noise is also capturing using the FDTT model. Okay? Done? So this is what I did in my PhD. 4 years I did. Right? 4 years I worked on this FDTT model only. Anyway, I developed the FDTT model. This is for copper. I developed the FDTT model for CNT also I developed. So before developing the CNT model, first I need to understand what is CNT, what is the properties of CNT, how it is useful for VLSI interconnects. So to establish that knowledge, I spent 6 months, right? For developing, I spent very less time, because once the model is ready for copper, the same thing you can apply for the CNT also. But understanding the CNT, it takes me 6 months time. Okay. And next, what I did, I extended for 3 lines. Okay, 1, 2, 3 lines I extended. Okay. As I told you, line 1 will see the inductance for line 2 as well as line 3 also you will see. Okay. Right. The magnetic field coupling between 1 and 2 is there. At the same time, between 1 and 3 is also there. Okay. But whereas electric field coupling, it is there between 1 and 2, but it is not there between 1 and 3. Correct? Because all the electric fields will exactly terminate to 2 only. There is no electric field sharing between 1 and 3. Okay? So that is what I want to say, that is what I want to convey. So when I am trying to publish this paper, one reviewer asked me one question. What is the question? Why you put L13? Why not C13? Okay. Why there is no C13? He asked me one question. Then I explained that. See what happened. You are sending the signal here. You are sending the signal on line 1. So whatever the electric field it is generating, it will terminate to 2 only. Okay. Suppose this length interconnect 2 is exactly at 50% of length. Suppose it is terminating at 50%, then C13 will also come. Okay. Because here 1 will see the interconnect 2 as well as 1 will see the interconnect 3. In this case, 1 will not see interconnect 3 because 2 is acting as a shield. It is completely covering. Okay. That interconnect 2 will completely cover the L3, right? It cannot see L3. 1 will not see 3 in terms of electric field coupling. But 1 will feel the 3 in terms of magnetic field coupling. Okay. So that's why you should place L13 also. Okay. Right? Electrostatic. That is magnetic field interaction. Right? Yeah. So then what I did, I analyzed the delay for all these cases. Right? You can see the way of accuracy I am getting. It is almost close to a single digit. Okay, right? Every time my model accuracy is a single digit, like 3, 4, 5, 6. That's it. Okay. So this is what I developed, and now just I will open my paper and I will see. So at that time I am the student member. Right? He is my supervisor, Rajesh Kumar Kaushik. He is from VLSI background. And the second guy is Dr. Amarendu Patnaik. He is from signal processing. Right? He guided me how to develop the FDTT models. He developed me how the crosstalk is induced in the on-chip interconnect. Right? So with these two people support, I have written this paper. Okay. So it is published in 2014. So now based on this, this is my starting paper where I started learning how to write a paper. Right. So after that, I have written so many papers. Okay, so this is my fundamental basic. So which software will you implement all? HSPICE and Matter. HSPICE, HSpice I have used for spice simulations and MATLAB for FDTT simulations. Okay. So this is what I conveyed first. So before starting my methodology, so what I conveyed to the reviewers that, so this is what actually gives. This is what actually gives from the CMOS driver, right? And this is what people will assume. This is what people generally assume, that they will assume this is a resistive driver. So that's why these two are not matching. So first one I cleared this. This resistive driver is different and CMOS driver is different. You cannot assume a resistive driver for CMOS. Okay, this one I cleared, and then I developed the model. So I mentioned all the steps, how I derived the equations, right? Once I derived the equations, then I explained how accurate my model is. I explained how accurate my model is. So I have placed so many cases, right? So many cases I explained, and so many comparisons I made. So finally they convinced and they published it. Okay. Okay, done. Right? And the second one. So time and frequency domain analysis of MLGN algorithms. So I have done the time domain analysis as well as the frequency domain analysis. Okay. So this is MLGNR, multi-layer stacked GNR. Right? This is the RLC equivalent model, right? That we developed. Right? It means using this model, we can do the simulations using any SPICE software. Right? You no need of using any quantum level tools, high-end tools, right? High-end processors, no need. You just use the RLC equivalent model and you design. Okay? And this is the ABCD model that I developed. ABCD parameters you already know. Okay? Right? So those things I developed, and based on that I plotted the frequency response, right? And I plotted the Nyquist plots, and I made my conclusion that MLGNR is better than SWCAT and WCAT. Okay? That's it. Okay, no high-end softwares, no high-end computers, just SPICE simulations and some basic knowledge of mathematics. That is sufficient to write the identity. Okay. So finally, I want to show my code so that you can do some work. Yeah. First you need to include the library files. Because you are talking about the CMOS inverter, you need to place the NMOS model library file and PMOS model library file. Because MOSFETs can be designed at different technology nodes. So 32 nanometer technology I inserted here. You can use any technology node, it doesn't matter. Okay. So you define the RLC parameters, and this is the way of writing the SPICE netlist. If you want to define the transistor, M is a transistor. So M1, M2 are the NMOS and PMOS of inverter 1, and M3, M4 are the NMOS and PMOS of inverter 2. There are two inverters, right? So this is one inverter and this is second inverter. First you will define the drain terminal, gate terminal, source terminal and bulk terminal. There are 4 terminals for MOSFET. You define those 4. And you define what it is, NMOS or PMOS. You define the length and width. Okay, done. And next you excite the inputs. This is your first input and this is your second input. And this is your supply voltage VDD, and this is secondary inverter supply voltage VDD. PSpice. No, speech files won't allow to include the library files. If it